So what I want to do now is I want to talk about some of the properties that are obeyed by limits. And specifically, we're going to assume that we have two limits, or the limits of two functions, f and g, and the limit of f is going to be L, and that's as z approaches z naught, and the limit of g as z approaches z naught is going to be m. Here, in order for this to make sense, we need z naught to be an accumulation point of both the domain of f and the domain of g at the same time. But f and g don't have to have the same domain, they just have to have at least z naught as a accumulation point in common. So with that in mind, assuming everything makes sense, in other words, all the limits are going to behave the way that we expect them to behave. So for example, we would have the sum, the limit of the sums is the sum of the limits. So what I mean by that is that the limit of f of z plus g of z as z approaches z naught is equal to the limit of f plus the limit of g as z approaches z naught. If you were to have the limit of a constant, I'm going to use the value alpha to denote a generic complex constant, but you can bring that constant out. So this is alpha times the limit of f as z approaches z naught, or in other words, alpha times L. If you were to have the limit of a product of functions, say f of z times g of z, the limit of the product is the product of the limits. So it would just be L times m. And then finally, if you were to have the limit as z approaches z naught of f over g, this will give you L over m, assuming m is non-zero. Okay, so all the usual limit laws that we expect are true. What I want to do is I want to prove some of these. I think what I'm going to do is I'm going to prove just item number 3. Item number 1 is proved in the book. Actually, items number 1 and 2 are proved in the book. I will show you how to do item number 3, and then maybe you can think about how would you prove item number 4. We just have to be a little bit careful about m being non-zero, but I want to let you sort that out on your own. I think it's important that you start to look at these proofs and try to write them down as much as you can. So I'm going to prove item 3. And again, that's that the limit of the product is the product of the limits. So we're going to assume that f and g have the property that the limit of f as z approaches z naught is L, and that the limit of g as z approaches z naught is m. And then I want you to think about, what does that mean in terms of epsilons and deltas? Well, that means that for all epsilon, there exists a value delta. So for all epsilon, there exists a delta, so that no matter what epsilon we pick, if z minus z naught is less than delta, then f of z minus our limit is less than epsilon. And what I want to do is I want to be a little bit careful here. So what I'm going to do is I'm going to write this kind of in 2 parts. In the first part, I'm going to write out all the details. And then what I'm going to do is I'm going to go back, and this is what most math books do, is they forget all the details, and then they go back and they show you, here's all the magic values that we need to make everything work out. I'll show you how they come up with all those. So let's just, for starters, let's just use epsilon 1 and epsilon 2. So for all epsilon 1, there exists a, I'll call it delta 1, so that if z is in the domain of f and the absolute value of z minus z naught is less than delta 1, then f of z minus our limit is less than epsilon 1. So that's what it means for the limit of f to be equal to L. And likewise, for all epsilon 2, there exists a delta 2, so that if for all the points in the domain of G, if 0 is less than z minus z naught is less than delta 2, then f of z minus our epsilon m is less than epsilon 2. And so what we want to do is we want to look at the product. So the thing that we want to say something about is the product f of z times g of z minus Lm, and we want this to be less than epsilon. So what I want to do is I want to think about how can we kind of massage this f times g minus Lm into something that we know. And what we're going to do is the often overlooked trick of adding 0. So what I'm going to do is I'm going to take f of z times g of z. We're going to subtract L times g of z. We're going to add back L times g. And then finally, we'll subtract Lm again. Let me move this over just so I don't have to write this on 2 lines. So minus Lm. And then what we're going to do is we're going to apply the triangle inequality. And so the triangle inequality says that if you have a sum of 2 quantities and you take the modulus, that's less than or equal to the modulus of the first term, so f of z times g of z minus L times g of z, plus the modulus of the second term, L times g minus L times m. Okay, and so let's see what's going to happen now. Well, on the first term that we have here, what I can do is I can factor out the g of z, and this is going to be equal to the modulus of g of z times f of z minus L. In the second term, I can factor out the L, and we'll end up with the modulus of L times g of z minus m. Okay, and then we want this to be less than, say, epsilon over 2. We want this to be less than epsilon over 2. And if that's the case, then we win, because the quantity that we have here is less than epsilon. So what we need to do is we need to pick our epsilon 1 and epsilon 2s carefully so that these always work out. And so what we're going to do is we're going to do a few things. First, let's look at just one step at a time. Let's look at this modulus of z times the modulus of f of z minus L. And f of z minus L, I just realized that I have a typo up here, I'm sorry. This f of z minus m should be g of z minus m. Okay, so it's g, sorry about that. So that's g that approaches m, not f. So that should have been g of z minus m up here. So what I want to do is I want to look at the modulus of g, and I want you to notice that based on this inequality, g is going to be bounded. So one of the consequences of having a limit is that the function has to be bounded by that limit. It has to be bounded on some open neighborhood of our accumulation point z naught. And what you could do is you could look at this. This is going to be, so g of z is going to be between m plus epsilon 2, so the modulus of m plus epsilon 2, and the modulus of m minus epsilon 2. But in particular, it's bounded. So I want you to notice that if z is close to, and I'll make this precise in a second, but if z is close to z naught, then g of z is bounded. And so it's less than or equal to some constant c for some real number c. Okay, so the modulus has to be contained in some disk of radius c. That's what it means to be bounded, and that has to be true given this inequality, right? G is not allowed to go to infinity because otherwise this wouldn't work anymore. Okay, so that's one thing that I want you to notice. So let's say that the maximum value that G gets is C. Okay, so let's say this a little bit more precisely here. Let's put all the pieces together. I think we're at the point where we can just put all the pieces together and you can kind of see how all the different pieces are going to fit, plug it in, and everything will be nice. What we're going to do is let's go through and let's do the proof again one more time, this time for real. When I say one more time, I mean actually doing all the details. So let epsilon be given, okay? And what we're going to do is since, I just want you to notice that since the limit of g is m, that implies that g of z is bounded. So then g of z is bounded on the set 0 is less than z minus z naught less than some delta. So it's bounded on the set delta for some delta. Let's call it delta 3, or let's call it delta naught. So for some delta naught. Okay, so since the limit of g is, since the limit of g exists, then g is going to be bounded on some open interval containing z naught. Let's say that the modulus of g is less than or equal to c if z is on that, in that neighborhood. So if z minus z naught is less than delta naught. Okay, then what we're going to do is it turns out that because the limit of f is equal to L, then there exists a value delta 1 so that if 0 is less than, let's see, z minus z naught is less than delta 1. I'm going to go back and talk about f. Then f of z minus L is less than whatever we want. And I want it to be less than epsilon over 2c, where c is this value, it's the maximum value that g takes in that open disk centered at z naught. Okay, so I can pick whatever positive number I want here. I pick this positive number. Okay, so that's the first thing. Also, there exists a delta 2 so that if the modulus of z minus z naught is less than, so if the modulus of z minus z naught is less than delta 2, then g of z minus m is less than, let's see, the modulus, it's going to be less than epsilon over 2 times the modulus of L. And I just realized that there's one case that I forgot to analyze when I was doing this ahead of time, and that's when the modulus of L is 0. In other words, when L is 0 itself. So we'll have to come back and we'll think about what happens when L itself is equal to 0. But actually, in that case, things are pretty straightforward, because if L is equal to 0, then it doesn't really matter what M is. Okay, so so we will talk about that. Okay, so we can handle that case separately. And maybe I'll do that in the next video, because this video is getting a little bit long. So let's just worry about what happens when L is 0 separately. Now, pick delta. So this is the trick here. We want all of these things to be true. We want g to be bounded by c. We want f of z minus L to be less than epsilon over 2c. We want g of z minus m to be less than epsilon over 2 times the modulus of L. And if all of those things are true, what we can do is we can just pick the smallest value, right? So in other words, we're saying here's some point z naught, okay? We know that around some neighborhood, g is bounded. Around another neighborhood, f approaches L, and around another neighborhood, g approaches m. So just pick the smallest neighborhood so that all of those things happen at the same time. And the way that we do this is we're going to let delta be the minimum value of delta 1, delta 2, and delta naught. And if that's the case, then all of the properties that we want to hold are true, because delta is less than each of these. And so therefore we can check. So therefore we can check, let's get rid of that. That if we take f of z times g of z, minus L times M, that's going to be equal to, well, we can just, since we already did the algebra, this is going to be less than or equal to the modulus of G times f of z minus L plus the modulus of L times G of z minus M. And we specifically pick this so that G is less than or equal to C. F of z minus L in absolute value, or in modulus, I should say, is less than epsilon over 2C. L is what it is. Actually, if L is equal to 0, then we don't have to do anything separate. Sorry. If L is equal to 0, then this is just, we don't really care what happens here. This is just going to be 0, and then everything works out nicely. So we don't have to do anything separate. But if L is non-zero, then this is going to be the modulus of L times epsilon over 2 times the modulus of L. And it works out that this is exactly epsilon over 2 plus epsilon over 2, which is going to give us epsilon. And one last thing I should say here is that I want this to be a strict inequality because these inequalities up here are strict as well. Okay, and so now all the pieces are in place, all the I's are dotted and T's are crossed. And there we go. So that means that the modulus of f times g minus lm is less than epsilon. So for all epsilon, we can find a delta so that this happens. So thus, and I forgot one more thing, sorry. If z minus z naught is less than delta, then f of z times g minus lm is less than epsilon. That does it.